This lecture is part of an online course of multivariable calculus, and I'm going to talk about the Greens Theorem. So let's take a vector field F, which is Pi plus Qj. I can write this in a vector notation and say that it's P and Q, where both functions P and Q are functions of x and y. Okay, we have seen that if the vector field F is conservative, which means what? Which means that F is gradient of some function f, then the integral of f dot dr over a closed curve C, that's the notation for the closed curve. So when C is the closed curve, this line integral is equal to 0. But what can we say about this integral, this line integral of f dot dr over the closed curve C, if the vector field F is not necessarily conservative? Necessarily conservative. Okay, that's the topic for Greens Theorem. So let me state the Greens Theorem. Greens Theorem says what? Greens Theorem says that the integral of a vector field f dr over a closed curve C, which can also have this notation: if f is P and Q, and for dr I write dx and then dy, this vector. I can also write this in the notation of P dx plus Q dy over a closed curve C. This integral, based on the Greens Theorem, is equal to the double integral over r of q with respect to x. So q is the coefficient of dy, which is the second coordinate of my f with respect to x, minus p with respect to y, the first coordinate with respect to y, or the coefficient of dx with respect to y, and then dA. So the question is, what is r, what is c, and what is the whole general ideas in here? So I'm gonna say that we have this line integral equals to the double integral if C is a closed curve, enclosing a region R. It's oriented counterclockwise. So these three conditions are basically the conditions for C. Okay, so then what are the conditions for F? And the vector field F is a vector field that is defined in the region R, and P and Q have continuous partial derivatives. Okay, then we have this situation. So you see, we have a closed curve C like this, and it's enclosing a region R inside, and so C is closed. It's very important that Green's theorem is defined just for closed curves. And we have a region R, and the curve C is positively oriented, or we can say that it's counterclockwise oriented. So if I want to have like more professional notation in here, I'm gonna say that C is positively oriented, which means what? Which means that it's oriented counterclockwise, such that R is on its left, Okay, let me move everything just a little bit and make it smaller actually. Okay, I'm gonna make it a little smaller. Very good. So it's very important that the curve C should be positively oriented. It means that if you walk along the curve C, the region R should be on your left. Okay, in that case we say that C is positively oriented or counterclockwise. Another criteria for C is that C here should be simply closed. For example, this is a closed curve, but it is not simply closed because it's cross itself. It is not simply closed, but for example, this curve in here, it's simply closed. So the curve C on the Greens theorem should be simply closed. It means that it shouldn't cross itself. Then another criteria for C is that C should traverse just once. So the boundary of R should traverse just once. We've seen before that we can define a curve C that, for example, moves twice along the curve C, but in the Greens theorem, if we want to use the Greens theorem, the curve C should traverse just once. Okay, and then all the other properties that we had for F was that P and Q should be continuously differentiable. Let me write this also in here. The criteria for F is that P and Q are continuously differentiable. Which means that they should have continuous partial derivatives, which means that P and Q should be continuous. They should have all the partial derivatives, and partial derivatives should be continuous. That's why we say that P and Q should continuously differentiable. Okay, so we should check all these criteria to be able to use Green's theorem, but for the sake of this course, we just pay attention not to this kind of advanced notations, but we just care that the curve C should be closed, it should include the region R, it should orient it counterclockwise, and the vector field should have partial derivatives that are continuous. Okay, just one small note is that if the curve C is oriented clockwise, we should just multiply by a negative sign. Clockwise, we should negate the integral. Okay, so that's all I wanted to say for Green's theorem. And in that case, for the line integral of a function over the closed curve C, you don't need to actually find the line integral. You can use Green's theorem and write this as the double integral of q with respect to x minus p with respect to y dA. Now let's look at one example to see how it works. So the example is this: evaluate the line integral over the closed curve C, which is right there. Starting at the origin, it goes along the x-axis, and then it goes along the unit circle and comes back along the y-axis to the origin. It's the closed curve of y e to the negative x dx plus 1/2 x squared minus e to the negative x dy. Okay, so for the solution, I see that I have a vector field f. This is my p, this is my q. So f is y e to the negative x and 1/2 x squared minus e to the negative x. That's the vector field f, and then based on the notation, dr is dx and dy. So I've been asked to find the integral of f dr. Okay, if I want to use just definition of the line integral, what I need to do is to divide the curve C into 3 curves. C1 is along the x-axis, C2 is along the unit circle, and C3 is along the y-axis. And then I need to parameterize each one of them. For example, C1, the parameterization x t y equals to 0, t between 0 and 1. C2 is what? It's unit circle, so cosine t and y equals to sine t, and then t from 0 to pi over 2, and then C3, which is along the y-axis, so x equals to 0, y equals to t, and then t is from actually 1 to 0, and then we need to negate that. So t starts at 1 and it goes to 0, and then calculate the line integral over C1, line integral over C2, and the line integral over C3. It's too much calculation if we want to use that. But since I have the integral over a closed curve, I can use Green's theorem. If C wasn't closed, I couldn't use the Green's theorem, and I need to calculate the line integral. Okay? Or there is another way. If C was not closed, then I checked, and if the vector field F was conservative, then I could use the fundamental theorem for line integrals. But anyway, C is closed in here, so none of this is gonna help me now. So I'm gonna use Green's theorem. So Green's theorem. And I'm gonna write this as the double integral over the region R, which is where? The region R is the region that is enclosed by the curve, closed curve C. That's the region R. Okay, of what? I need to write this of q with respect to x minus p with respect to y dA. That was the formula. So q with respect to x. Take derivative of that with respect to x. It would be x plus e to the negative x, right? Actually, let me write this. Derivative with respect to x of 1/2 x squared minus e to the negative x minus partial derivative of p with respect to y e to the negative x, and then dA. Okay, I'm gonna move this one a little bit. Okay, so now let me calculate that. double integral over r. Derivative of that with respect to x, it would be x plus e to the negative x minus derivative of this part with respect to y is e to the negative x dA. So these two would be cancelled. I get what? I get the double integral over r of x dA. But look at r. R is part of a disk. That's why it would be easier if I switch into polar. So I'm gonna switch into polar, and I'm gonna write what? Instead of x in polar, I can write r cosine theta. Instead of dA in polar, I can write r dr d theta. And then look at the region R. In this region, R in polar would be from 0 to 1, and theta would be from 0 to pi over 2. So R is from 0 to 1, and theta is from 0 to pi over 2. Okay, very good. So I'm gonna keep writing the outer integral, and then for the inner integral, what do I have? I have r squared dr and then cosine theta d theta, right? So these are the constant that I have, and then the integral of r squared dr, actually let me just calculate the integral, would be r cubed over 3. R is from 0 to 1, and then cosine theta d theta. So I'm gonna keep writing the outer integral. Plug in 1, 1/3, plug in 0, it would be 0, and then the integral of cosine theta d theta, it would be 1/3. The integral of cosine is sine of theta from 0 to pi over 2. So sine of pi over 2 is 1, sine of 0 is 0. So I just get 1/3 times 1. So that's the answer for this example using Greens theorem, not the line integral. Okay, so let me give you a note. We can actually apply Greens theorem to region with holes. Okay, so we can also apply Greens theorem to regions with holes. But we need to be careful about the direction. Let me give you just one example on that. The integral of y cubed dx minus x cubed dy, where C is two circles with radius 4 and 6 centered at the origin. Centered at the origin. Okay, so let me graph the region of the integration. This is x axis, y axis. So I have two circles, one with radius 6 and the other one with radius 4. It's not a good scale, but that's okay. So it's with radius 6, this is with radius 4, and then the integral of C is actually the integral over C1 plus the integral over C2. Okay, so how do I orient the surfaces? So if I want to use the Greens theorem in here, so this is C1, oops, this one is C2. Okay, I make C1 counterclockwise, so that the region R, that is the region in between of these two, is on its left. But for C2 to be positively oriented, C2 should be clockwise. C2 should be in this direction clockwise, so that if we move along C2, the region R, which is the region in between two curves, is on its left. Okay, so it's equal to what? Using Greens theorem, it's equal to the double integral of R. So this is using Greens theorem. And it's the double integral of the partial derivative with respect to x of q. This is q, this is p. So this is p, this is q. So of negative x cubed minus the partial with respect to y of p, which is y cubed, and then dA. Okay, so let me calculate that. Derivative of that with respect to x, negative 3x squared, minus derivative of that with respect to y is 3y squared dA. So I can factor out the negative 3. So I have the double integral of r x squared plus y squared dA. I'm gonna switch it into polar because my region of integration is part of a disk. Okay, so in polar, what do I have? I have negative 3, the double integral of, this is r cubed, r squared, and then dA is r dr d theta. R is from 4 to 6, and then theta, to make it the full circle, is from 0 to 2 pi. Okay, I'm gonna write the rest in here. So I have negative 3 theta from 0 to 2 pi. Then I have r to the power of 3, so I get r to the power of 4 over 4, r from 4 to 6, and then d theta. So I have negative 3 over 4, and then plug in 6 minus plug in 4 to the power of 4, then the integral from 0 to 2 pi of d theta. Here I get a theta from 0 to 2 pi, which would be just 2 pi. So this is negative 3 times 2 pi, which is negative 6 pi over 4. Simplify that, it would be negative 3 over 2 actually. Negative 3 over 2 times pi, and then 6 to the power of 4 minus 4 to the power of 4. That's how we use Greens theorem when we have a hole. On the next video, we're gonna see applications of